Here? Test, test, can you hear it?
Okay. For the last talk of today, which is of course not the last day of the conference, so we've got more coming tomorrow. Happy to introduce you to Andriy Nevidomskyy. Andriy actually did his PhD at Cambridge, and by going by various places, which I'm happy to say did include Rutgers. He is a professor at Rice University, and today he's going to tell us about spin supersolids and frustrated magnets. So, thank you.
Thank you, Piers. Thank you, Frank, Gunnar, all the organizers who I forget to mention for inviting me. All right, so I'll aim for, as I can, a pedagogical talk. So please do interrupt me with questions. They're very, very welcome. Can you hear me at the back? If I start speaking softer, just shout out. So tell me to speak up. All right, so most of this work was done with a student, Yishu, at Rice University, and a former postdoc, Shovik Su. And then there are other collaborators who I mention as I go along, including some experimentalists. So this talk is going to be of two parts. And the first one is going to tell a story of a Bose liquid. Okay, and I'll tell you in a moment what that is. And so as a prelude, so we just heard the talk about what happens if you take a Fermi gas and you apply interactions, right? And so there's a question generically, what happens? You see, if I take a dense Bose gas, Landau taught us that in the absence of phase transitions, I'm supposed to have renormalized quasi-particles, and I end up with a Fermi liquid. And if I start with the dense Bose gas, then going back to the seminal paper of Bose, which goes back by now, what, slightly more than 100 years. Yeah?
Online audience says, can you
turn up the volume? Okay. So that requires me to figure out where my controls are.
Use the microphone.
It is being used. It's just a question of why it's not. Oh, I see. There is an input volume that I can crank up. Is that better? I would imagine that should work, right? If they still can't hear it, there isn't much I can do.
You can hold it.
better.
Oh, yes. Good. Excellent. Let's see. Somewhere here there should be. That's the one. Okay. Thank you. Yes. All right. So now there are exceptions to this, and one of them is a one dimension, which is, you heard the talks, well, 2 talks back, that you can have large energy liquid, and then you could use the techniques like bosonization, and generally the concept of quasi-particle breaks down. But what happens in higher dimensions? So for this, I need to click somewhere on the screen. There we go. So what happens in higher dimensions, in 2 and 3 spatial dimensions? And this is the problem of going back and forth with the zoom. There we go. So if you start with the fermions, then of course there is a whole field of which Zilka spoke of, non-Fermi liquids. And I'm not going to talk about those at all. Okay, so this is not the subject of today's talk. Instead, I'm going to ask what happens if you have dense Bose gas with interactions. Can you somehow avoid Bose-Einstein condensation? And so at first glance, the answer might be no, but if you look at this, around about 20 years ago, Ron Paramakanti, Balance, and collaborators had this interesting paper where they coined the phrase of Bose metal. It's a bit of the misnomer. I mean, what do you mean by metal? We sort of used to have metals being made of fermions, electrons. So here, don't think about this seriously. It doesn't mean it's a metallic system. In reality, it just means it behaves like a metal, but it's made out of bosons. And I'll try and qualify what that means. And so the question, what I'd like to convince you is that possibly the best candidate to probe this kind of physics is actually frustrated magnets. And the logic behind this is the following. Imagine I give you a magnet. I don't want to be a ferromagnet, but any other antiferromagnet would do. Right? It doesn't have to be Niel. Choose any lattice you want. Eventually, if you apply a strong enough magnetic field, you end up polarizing the system. Okay, so that's intuitive. And then below some critical field, well, you will have whatever the ground state of the magnet that is. Okay? Maybe if you're lucky, you get a quantum spin liquid, like Seamus told us about Herbert-Smithite, but more generally, you have some ordered state. Now, it turns out that there's a transformation you could do where you go back or transmute your spin operators, the raising and lowering operators, into creation annihilations of bosons. Now, in order to satisfy the proper permutation relationship, this only works if the density of bosons is small. And so this whole approximation only works close to where the density of bosons, which is tuned by magnetic field, is small. Now, why is it tuned by the field? If you look at what stands here, this is your SZ. So if my field points down, I have a saturated value of moments, which is -1/2. Okay, so everything points, let's say, up in this case. And then if any deviation from that is precisely my boson number. So there you would expect that as you go from the left to the right, you have a BEC universality class. So if you're above the transition, one way to think of it is that you have chemical potential that's positive, and as you go below, the chemical potential touches the zero, and you end up Bose-Einstein condensing this. Okay? So this is well studied experimentally. Here's a recent example, although there are many more. This is from Yosuke Matsumoto from Hida Takagi's group at Stuttgart, where recently they've shown this interesting material, yttrium trichloride, which as you go through as you go through a saturation field, which here is about 6 Tesla, you see a transition from some long-range order. Don't worry if it's Heisenberg or XY, there's the details, but you go into fully polarized phase. And they go at great lengths classifying this transition and convincing you that this is BEC universality class. All the exponents work out exactly how you would predict them, and everything works wonderfully. So the question I'd like to ask is whether what I just told you, is this always true? Now, I don't know how many of you know this gentleman. Ian Hinchliffe is actually a British-born physicist, but he's at Berkeley Lab. He's a high-energy physicist. And back in the 1980s, he formulated this principle, that there is a yes or no question in the title of the paper. The answer is no. There turns out to be an equivalent, which is much later, about headlines. This is from journalism. Okay, so there's a headline in a newspaper you're reading or whatever, online article. The answer is no. So recent examples, for instance, this is from BBC News a week ago, right? So I hope the answer is no, and we'll still see Djokovic, but we'll see. Are there any Canadians in the audience? Okay, so I'm not going to offend anybody. I hope the answer to this is no.
Wait. Is he serious? Yes. 51st state? Hope not. Yeah.
I just hope he's not serious. All right, anyway, so now I pose the question.
Is he crazy? Yes.
Right. Is this always true? So, based on what I told you, perhaps the answer is no. And that's what I'll try and convince you of today.
Andriy, just
Yes.
a stupid question.
Yes.
In this example of your yttrium trichloride, what are the bosons that you're condensing? Because it's just not immediately clear to me.
Yeah. Okay, so I want to make a distinction from the talk that you may have heard from Amir Yacobi earlier in the conference this week, where what he had is a ferromagnet, and then he had some thermal population of bosons, of which there are few. They're just spin waves that are sort of floating around. And then what you do is that he created sort of inverse population of them. He pumps them, in his case by having platinum wire and essentially driving the bosons. Or when he was answering my question in the earlier work by Demokritov, you send an optical pulse and you excite a bunch of, you excite to a high optical transition that then decays into Q and minus Q and creates a bunch of bosons. And those objects condense. Here, none of that is happening. When I talk about bosons, they are not spin waves, although you could think of them as that if I'm in a fully polarized state and everything is aligned, you ask what are the excitations just slightly below the critical field. So I have a little bit of leeway. My spin can jiggle a little bit because it's not fully polarized. Those objects, those spin waves around fully polarized state, that's what I'm condensing.
It's the same thing. It's a spin wave.
Right, but yes.
Okay.
My point, so there is some semantic distinction in a following sense, that if you ask Amir how would you probe this Bose-Einstein condensation, he would need some very complicated apparatus, colors. Here you ask news progressives, how do you measure this? Well, it's just ordered magnetization, that's all there is. So this fancy language of Bose-Einstein condensation in this language is nothing but just ordered magnetism, right? So I want to dispel the notion it's not mysterious. Okay.
Thank you.
But can you somehow avoid this? So here's a model I propose to look at. You choose a lattice, but in this case I'm going to choose a square lattice, 2-dimension for simplicity, and I have some G1, G2, G3. Heisenberg interaction, spin half. Okay, easy. As Sasha Chernyshov, a friend, likes to say, well, before you try tell me anything about quantum, tell me what the classical phase diagram is. And this is what classical large S calculation would tell you. It will tell you that if G2 is small, you have an AL phase. It becomes stripe or columnar ordered, if you will, pi 0, 0, pi. And here you have so-called spiral phases. And even at the classical level, that's a rich phase diagram. For instance,
This
you could
is in 2D?
2D. For instance, you could study what happens along spatial lines, where there is some fine-tuning of points. There's a concept of spiral classical liquids that you could, some people have studied. But here I'm going to ask the question about, now that I told you what the classical system is, what about spin half? What about the quantum methods? Okay? And that question is much harder. And so that paper by Arun Paramakanti, Balens, and Fisher, going back more than 20 years ago, was trying to answer that question. And they were focusing on a particular slim region of the phase diagram, and I'll tell you more about what they found. Subir Sachdev and collaborators were focusing on this region of the phase diagram, trying to answer what happens there. And there's interesting questions of do you confine quantum criticality and exactly what happens as you go from ordered Néel state to possibly valence bond solid. The physics is rich. And what makes this difficult, despite the apparent simplicity of the model, is that you can't solve it exactly. Of course, you could try and do exact normalization or heavy numerics, of which I'll speak later, such as DMRG or tensor networks. But what we'll try and do is apply external magnetic field to this. And the idea is that to control this, and this was the result of the postdoc Shovik, is that what we'll try and do is this substitution that I just mentioned. And what will happen is that this model, which is written in terms of the spins, becomes a model of bosons. And of course, there is a kinetic energy term over here, and there is interaction between them. Now, they're so-called hardcore bosons because you want to preserve the size of a Hilbert space. You don't want to be able to sit on top of one another, so you want a repulsion which formally goes to infinity. So U here is extremely large, okay? So you can't do simple perturbation theory. What do you do? Right? So let me first tell you about what the kinetic energy term does before we talk about the interactions. So imagine parking yourself somewhere in a phase diagram. I'm in an L phase, and if you look at what is the dispersion of this spin waves around that point, it goes as k squared. And as you now imagine moving somewhere across the phase diagram, something interesting happens. You go from a point where there is one point, let's say pi pi, to somewhere where a different point in the Brillouin zone is where those magnons or spin waves would like to condense. Okay, so that transition is nothing else but the Lifshitz point. We're used to thinking of Lifshitz. By the way, this is Ilya Lifshitz. It's a younger brother of the Lifshitz who's Landau Lifshitz, but equally famous. So Lifshitz-Korsavich formula is this Ilya. By the way, he's born in Kharkiv. He's my compatriot and did his PhD with Landau. But going back to this, we are used to thinking about the Lifshitz transition in metals as a topological transition of the Fermi surface. It's very similar here. Ignore the fact that these are bosons, fill it up with finite chemical potential. You have a single Fermi pocket around, let's say, pi pi in a corner Brillouin zone. And now you have two Fermi pockets, which are now at some points that are not at pi pi. How do you go from one to the other? Well, exactly in between, something interesting has to happen, namely your dispersion has to flatten. Quadratic term disappears and you get generically a quartic term. So you could describe it in a continuum theory, if you want to be fancy, by putting some effective mass. I'm going to call it a Lifshitz mass, and when that number goes to 0, I'm losing all the second derivative, and I'm only left with higher order. Or you could write it in kx, ky, it's your choice. So the first thing I could tell you about this is that in the low density limit, the bubbles, those bubbles of the Green's functions that you saw in the previous talk, they're proportional to the boson density. If the boson density vanishes, those bubbles also vanish. And so that tells you that if you're trying to do perturbation theory, 1 loop, 2 loop, 3 loop, RG or whatever you'd like, those corrections become less and less important. So the model becomes more and more solvable, and that guarantees that, for instance, the critical exponents that you get at the bare tree level actually remain exact. Okay, so that tells you that there are no first-order corrections in the particle-hole channel because of this. This fact, in fact, was pointed out. Well, let me first do the slide, and then I'll tell you the historical interlude. So you see, if you go this point, you will find that the critical exponent Z is equal to 4. And that's an unusual. You see, boson could not have predicted bosons which would disperse quartically with momentum. That's not something that's usual, right? That's not what we write down in Schrödinger equation. It's p squared over 2m, and that term is gone. All I have is p to the power 4. And that has immediate consequences that, for instance, if you look at the so-called beta exponent, how does the boson density depend on field? It goes like 1/2 instead of the BEC, which is 1. Okay? So for instance, here's where we've done some heavy numerics using tensor networks, where the exponent is not exactly 1 for, and we understand why, there are log corrections in 1 plus 1, in 2 plus 1z. Essentially, you've got a exponent that dives down, and again, the value is not exactly 1/2, but that's the expected value. Now, what I told you about the particle hole being exactly solvable point was done by this gentleman over here, who had a fantastic name, Spartacus. That was his first name. So Spartak Belayev was the first who was studying dilute Bose gases for different reasons. He was actually interested in plasmas. So we saw pictures of tokamak yesterday in Seamus's talk, so this was actually what he was working on. He pointed out that in the absence of those bubbles, there are still interactions that you might worry about in the particle-particle channel. And for that, it's sufficient to just sum the series of so-called ladder diagrams. Okay, so the details aside, what it allows you to do is have control over the analytical expansion with no fudge parameters needed. Okay, so you don't need to argue when is it true, when is it not true. It turns out to be asymptotically exact result. The catch is it's only true at, strictly speaking, when H is equal to HC. So when you're right at the saturation field and you have almost no bosons left, that's when this result becomes exact. And if you turn the crank, and we've done the RG using the epsilon expansion, so here we do it at one loop, you find that there is an interesting new critical point with some emergent value of the constant that depends on the values of the Bayer parameters of the model. So essentially, the picture becomes this. So you might worry that all of this is very fine-tuned, but you see, if you imagine starting, whoa, this one, way okay, spoiler ahead, sorry. So imagine that I have my phase diagram and I'm trying to scan it in this way, and I park myself outside of this critical cone. So we've done calculations at finite temperature. I could tell you a lot more details, but qualitatively, this is the picture. If you're over here, remember in 2 dimensions at finite temperature, we don't actually have true long-range order. Instead, you have a BKT transition. So this line, this orange line of this cone, that's my BKT line, below which I start having quasi-long-range order. Truly, at t equals 0, you end up with long-range correlation. Now, outside of this cone, as long as you're below BKT, you have this physics of the EC. You have a density of bosons that scales linearly with temperature. You could write down scaling equations for instance, Green's functions, and you know everything about the problem. What happens is when you get into the basin of attractions of this critical point, that's where the new exponents kick in. And for that, you don't need to be exactly fine-tuned to the line. As long as you're within that critical cone, you'll be fine. The slope of this cone is controlled by the Bayer parameters of the model. And so in principle, experimentally, even if you're not exactly at G2 critical by tuning field, there's hope that you should be able to get that. Okay?
This is a BKT transition. There should be some pairs of topological defects that bind and unbind. What are they in this system?
So those would still be true. It would be exactly that. So you will have a sort of paramagnetic background. So all my spins have a very strong component pointing along the field. And if you ignore that, then you say, okay, but that's obvious. What about XY components? Those would be the XY model, which you could parameterize by the angle if you wish. And that XY model, classical XY model, would exactly be your BKT. So you would have vortices and anti-vortices formed in terms of the XY components of the space. Right? So you could imagine them having a topological vertex, kind of like a hurricane, and that would be your vortex, and you would have anti-vortex. Right? That physics all happens at high temperature. By the time you reach to over here, your vortexes and anti-vortex pairs have condensed or have annihilated each other. You have none of those topological excitations present. That's your BKT transition.
Andriy, are you inherently in a 2-dimensional limit here?
For the purpose of this talk, yes.
Okay. Does it project up to 3, or
Yes.
it does?
Correct.
Okay.
You could do the same analysis in D equal 3. You will see there will be differences when it comes to the details of the scaling exponents, but generically, whenever you have a Lifshitz transition, in the sense that I described, which generically you need some G1, G2, G3, you need something that looks like a spiral, right? So Goldman, not Alan Goldman, but the other one who's at Ames Lab,
Yeah.
he's interested in some materials that have this sort of spiral in third dimension.
Yeah, David Johnston in particular.
Right.
Yeah, sure, okay, thank you.
All right.
So equal 4 means you are always above the upper critical dimension. You said you did some RG.
Correct, because in a particle-particle channel, so these are interacting bosons and the interactions are strong. So yes, you're formally right. D plus Z, which is larger than 4, should be, right? You should be above the upper critical dimension. But you have to rethink how you do it because you have K to the 4 dispersion instead of K squared. So it turns out that in a particle-particle channel, you still need to work hard to compute those corrections. You could also do some numerics, which I'll spare you the details. Instead, let me ask the question, which is really interesting. Can you really have boson metal at finite boson density? So now the vertical axis is my field, and this line is my H saturation. So if I go above, I just have field polarized magnet, and below, I go from here to here. So if I now were to start, let's say somewhere here, and imagine tracking the parameters of the model, I cross this Lifshitz transition. I go from the L to some spiral phase or, what have you. And the question would be, can I have something interesting in boson metal at finite density, right, over here? And I'll try to convince you the answer is yes.
Okay.
And what that will be is something which Seamus will be happy is a quantum spin. Yes?
Why are your boundaries between your phases vertical? Often with
Yeah.
field, you can have cascades of transitions. This seems to be artificial and perhaps limiting.
Yes. So I am being agnostic as to what happens when you're far below H saturation, right? This is where indeed you could have plateaus, depending on the physics you've got, you could have interesting questions happening. But as long as you sit very close, slightly below saturation field, that's the picture.
Okay, fine. So if they have a slope with H, who cares? I'm just really cruising by the critical field.
Precisely.
Lovely,
So if
thank
you would like to do sort of an experiment on that, I'd suggest you choose somewhere where critical field is not too huge,
Yeah.
where you could stay below the saturation
Lovely.
field and do whichever measurements you'd like. So what would you measure? Well, I would argue that what you'd like to do is to measure in some sense boson density. Now, what is that? Remember, boson density maps onto a Z, right? Or deviations of a Z from being fully saturated. So my boson being condensed, quote unquote, just means I have XY component of magnetization. So if you could measure XY component of magnetization, that would be your boson. And I'll do the same thing we do when we describe superconductors. I'm going to say that at finite density, I will have an amplitude and I will have a phase.
Yeah. Is it okay to interact?
Oh, yeah, you should. But I don't have any cookies to give.
Yeah. Cookies.
Yes. Well, I like it. Yeah,
You
those
like cookies?
incentives, yes,
Okay.
I just like cookies. I'm a theorist.
Doggy treats. You were saying measure the XY component. That's a pain in the ass. Okay, I mean experimentally sometimes. On the other hand, can't I just measure deviation from the saturation? So basically measure how far
Yes,
I
you
am,
could.
because longitudinal magnetization is much easier to measure experimentally.
Yes.
And I think that would be an adequate proxy.
I agree with you.
Okay.
The only caveat I would make is that at any finite temperature, as you know, of course, you will
Yeah,
have sort of
yeah,
Brillouin
yeah.
function. You
But
have
I'm
to be
well below the
careful.
ordering temperature like
That's
this.
right.
Okay,
Yes.
thank you.
Okay. All right. So what you could try and do is to write an effective action for those fluctuating phases. I mean, if you think this is what we do in Ginzburg-Landau theory of a superconductor. The phase rigidity is nothing else than the statement that the zetas or correlations of the zetas are long range. If I probe a phase here and I probe the phase far, far away, they're in sync. That's my superfluid or superconductor. And if you try and solve this model, you will see that if you have this Lifshitz mass, which is non-zero, which means you're far away from that critical cone, you will see that indeed the correlator between the bosons becomes constant and you have Bose-Einstein condensation. This is nothing else but off-diagonal long-range order in the language of bosons. Or if you ask what is in terms of spins, it just means long-range order. You see this S plus S minus correlator is what Peng Cheng, for instance, would measure in neutrons. Okay, that's proportional to the spin structure factor. You measure static spin structure factor, just diffraction, you will see a Bragg peak, that's that. Now, what happens if there's a Bose metal and this value is exactly 0? Well, then you could prove that there is no Bose-Einstein condensation, there is no ordered MX. So if all you measure is a deviation from a Z, you will conclude, well, I'm not exactly at saturation. I have non-zero XY component. But it doesn't tell you, is there phase coherence? Are those phases rigid? If I look here and I look over there, do my XY spins all align in a particular fashion, right? And the answer here would be that actually if you compute this, you will find that this function actually requires an algebraic dependence, power law. And if you track it down, like where the heck does it come from? It's because of the density of states being divergent. So this whole complicated story boils down to the fact that my bosons have quartic dispersion.
Andriy,
Yes.
excuse me for stupid question. What kind is omega squared?
So the omega squared is my Lifshitz, oh sorry, where? Over here.
Yes.
Yes. So this is the inverse Lorentz function if you integrate out the amplitudes and you're only left with the phases. I can show you in detail.
Yes,
I just
yes,
don't
yes.
have slide here.
Don't worry.
So,
Would this happen in a three-dimensional system, the divergent density?
okay, very good. So if you do the same thing in 3D, the density of state that would appear over here would depend on this boson. So if you do k to the 4th, but you are in 3 dimensions, gosh, instead of 1 over square root, you have like epsilon to the power minus 3/4 or something like this. So I think it would still work.
So I'm a little bit confused. So you try to tune the anti-Fourier margin into a Fourier margin, right?
Polarized phase, yes.
But I mean, I thought anti-Fourier margin for the linear dispersion, right? In the local limit.
That's without field, but when you're very, very close to the saturation field, instead of having Goldstone modes that are linearly dispersive, they curve like k squared. So that's very, very close to saturation field. Correct, well, very close to the critical field. If you go
But below
deep
it.
in the ordered phase, then yes, you will have your Goldstone modes that would generically be linear. But very close, you have to go from k linear to k squared. And you could show it rigorously at the saturation field.
You assume interacting bosons at finite density, right?
At finite but small density. So all
You can integrate down the density fluctuations, their mass, and you get omega squared.
precisely, exactly. That's exactly what happens over here. And if you try and do the same calculation for regular bosons, k squared over 2m as we used to, you would not get divergence. You would not get this n of epsilon, which is like, for instance, constant in 2D. And so then when you integrate this function, you will have something which is fine. This has infrared divergence. It secretly looks like Lagrange liquid in the sense that, effectively you have some quantities that have infrared divergences in them. And the consequence of this would be that if you look experimentally, let's say in neutrons, at the spin-spin correlation function, then you will find that actually it decays as a power law, provided you're at length, which is cut off in practice by this Lifshitz correlation length. Right? So this Lifshitz correlation length depends how far you are from the critical point. If you're strictly at the Lifshitz point, this C diverges and you always get power law. In practice, if you're slightly detuned, you might get exponential cutoff, but initially you will have this power law. What's interesting is this power law is not fixed. If you ask me, what is this omega Andriy? Is it some, okay, you give me it's a critical exponent, what is it? So the answer ends up being that actually it sensitively depends on the bare parameters of the model. It depends on the applied field, interestingly enough. It depends on the values of J that you have over there. So there is some 1990s paper from Supersolids and collaborators that call this a zero-scale criticality, where when you do the RG, instead of heavily renormalizing the parameters, your critical exponents are determined by your bare UV parameters of the theory. So there is some interesting deep physics that I don't want to go too much in detail, but the conclusion I want you to get out of this is by having this quartic bosons, the dispersion being strange, you have a power law which tells you there is no Bose-Einstein condensation, bosons look like they're fluctuating at all times, and their correlation function, density-density, decays as a power law. That's what they mean by the boson metal. That's the language that was invented by, I guess, Leon Balance and Arun. Okay, so
Andrew,
yes,
if I'm trying to think of systems that would show this, many systems that are anti-ferromagnetic applied field have first order transitions, metamagnetism. Those are ruled out, you're not interested in it, because you want a second order.
nor
So
do I want a nor do I want a ferromagnet, because
No,
then
no,
you
no,
just,
but
you don't have a transition at all.
then if I'm just thinking about this, you want an MH at low temperatures that is sort of linearly rising and then sort of bending over to saturation.
Yes.
Something is structural. Is this correct? Could I use that as an experimental sorting parameter for what systems may possibly be applicable for this?
Well,
Because any little
Yes.
jump, that's first order,
Yeah.
don't care.
ideally, yes, I morally yes, but I think you need more. You need
Oh,
to
I'm
be
trying
somewhat
more.
close to what I call a Lifshitz transition. So you need to be frustrated enough, or you feel like, oh, I'm not, like you look at neutrons, it's like, oh, do I see some vague spot near pi, but also something near pi 0? Is there coexistence? Are there two phases? That would be more of an indication something interesting going on.
Be careful, because if you think of Syria monoantimonide, the classical devil's staircase, you have in your HT phase diagram 15 different ordered phases. No, so
Yeah.
lots of things are close to each other, but they're almost all first order phases. So just proximity to competing phases is enough. For me, the one vital ingredient is this has to be a second order transition and therefore no discontinuity in MH, correct?
Correct, yes.
Okay.
I mean, maybe I could say more that ideally you don't want to have Ising magnets. That's why you tend to get those devil's staircases with many, many phases.
Of course.
Here I have a degree of freedom which is U1. That's what condenses. So
Right, so I mean, if it's a rare earth, I'd want gadolinium, but that's still probably too large of a moment for you.
Exactly. All right, so what I told you is a story about a model of a quantum spin half system, which generically many people tried solving it, and it's very, very hard generically. What makes us able to make progress is the fact that we apply very high magnetic fields, such that you're just below the saturation field. And in that asymptotic regime, the theory becomes exact. And I don't mean approximately exact, I mean exact. So the critical exponents you've got are God-given, that's what they honestly are. We find new universality class with this zero scale criticality, which depends on the parameters of the model. And we find that as long as you're within this critical cone, you find an interesting intermediate coupling fixed point. I can tell, and perhaps the most interesting conclusion is what I told you lately, or lastly, is that you have a power law behavior of correlations, which you could think of it as a Bose metal in the language of bosons, or algebraic spin liquid in the language of spins.
Excuse me, this for high correlation comes from negative M when the spectrum is a mode, right?
No. Oh, okay, so good point. So this finite C comes if you're not exactly at this transition, you're detuned.
Yes, I understand.
Now, there is something interesting that Alexei points out over here, that, okay, you see this blue line descending over there. So it turns out that this point over here, which I carefully stayed away from, is special. If you go from the L phase right through here, what you find is that instead of excitation being at one point, pi, they morph and tend to form what people call a mold. You have a continuous line of points in a Brillouin zone where your bosons want to condense. And that's very unusual. So Andrew would know this in in AMO context, as some people talk about fractionalized condensates. You could make this mold potential with synthetic spin-orbit coupling in optical lattices. And there are interesting questions about how to treat that. It's sort of a quantum analog of a Berezovsky system where you have the whole mold, you have continuous degeneracy. In my Lifshitz case, I had either one point on the left or 2 points on the right? So I didn't have to deal with this mold geometry. That stuff is genuinely complicated. Alexei Kamenev with Glasman have tried to make progress on this. There are other papers from other people trying to do this numerically. It's a hard problem. It smells like two-dimensional or high-dimensional bosonization because you have an entire segments sort of like Fermi surface almost, I want to say, except as the bosons.
But surely you have a similar problem if you go toward zero, because then again you have a triple point of your phases.
Well, right, but at least here I don't have a mode, I have sort of one point where you go from here to a stripy face.
But you have spiral close by also.
Right, I'm just pointing out that there is something special about this blue line dissecting here. This point, so yes, there are spirals and then there are spirals. And if you look right in the vicinity of this point, this is where you get this mode geometry.
It's not associated with the fact that you have 3 magnetic phases degenerative.
No, it's not, well,
Okay.
yes, it is a triple point in that
Yeah.
sense, and you're right, it's tied to that.
But then you have a triple point at zero also.
Where is the surface? Oh, I see what you mean, the spiral, okay, I hear
You
what
have Neal, spiral,
Yeah,
and
yeah.
stripe. Don't
Yes.
you get similar complications?
Turns out that no, I
Interesting.
can show, I can
Okay.
show you to you.
All right.
Yes, sir.
Do you see a way to engineer maybe Lifshitz transition where you get a kx squared ky to the 4
Yes,
expression?
well, exactly, so as long as you don't have quadratic terms, it doesn't really matter. So for instance, near this point over here, the dispersion looks like kx squared times ky squared.
You would probably need another scaling exponent between different spatial directions.
Yeah. I mean, it could be that AMO systems is another way synthetically to engineer something like this. If you could, because there you have maybe more malleability, more knobs to tune your hoppings on the optical lattice. As Paul, you pointed out, there is some serendipity. Mother Nature, not that nature, Mother Nature gives you a material, and then you are stuck with whatever G1, G2, G3 there are, and then you say, well, maybe now I need to go back and grow a different material if I want to tune it. Maybe if you're lucky, you could do intersubstitution, or you could try to apply pressure, try to tune those parameters, but in practice, they don't move by much. So that's what I'm saying. You have to be pretty close to the phase transition or phase line, and then hope that by tuning it a little bit, you get close enough. So I don't have great experimental suggestion for how to reach this, but in the second part of the talk, I will. So this is about an actual material which was studied in the lab, which was synthesized only about less than a year ago. But first, let me tell you why I have supersolid in the title. So the experiment, okay, I promised I'll show you the material first. So this is a material based on cobalt. This is cobalt, I want to say, is it 2+? Okay, it's maybe 3+. It's spin half. So it's a cobalt spin half system that forms layered structure. And if you ignore the stuff that's in between the layers, the selenium and the oxygens, essentially you end up with triangular layers motifs that are separated quite a bit in the vertical direction. So the C-axis is quite large, and you have, if you focus your attention only on cobalts, you end up having this perfect triangular lattice. And by perfect, I mean the crystallographic symmetry is such that it's undistorted, right? It's high enough symmetry. This was first synthesized independently by a group of Andriy Nevidomskyy at the HA, Zurich, and by Colin Brochel. And these two papers that appeared on arXiv almost simultaneously, there is some bit of war going there that I should not go into. They both had the word supersolid in the title. Okay? And I want to expand, okay, so why these two experimental neutron scatterers zeroed in on supersolid? Where is that come from? So you see, if you look at the diagram of helium-4, of course, we know this is by now, almost 120 years ago, Caroline Onnes reached this point over here where you go from a gas into a liquid. But then if you go further, and this had to wait another 30 years, this is where you end up having a superfluid transition. Now, further, if you apply pressure, you could have a solid. And one question is, how do you go from solid to the superfluid? And there were some suggestions going back to some work by Andreev. This is the same Andreev as the Andreev reflection, Andreev and Lifshitz. This is, by the way, also Ilya Lifshitz, the one I promised you I had a picture before. As well as British physicist Chester and Anthony Leggett, who suggested, I mean, Leggett's article is probably, right, it's in the title, can a solid be superfluid?
No.
So could you have a superfluid property while maintaining solid-like rigidity? And so there are some old experiments, this is 1979. I forgot to put in the reference, but as you could see, probably from GETP, Journal of Experimental Theoretical Physics. Kashyshev saw that if you sort of look at the menisc of where you have a solid just about to melt, there are some strange waves and there are some indications that maybe these defects kind of float, and so you have a strange supersolidity where it's neither liquid nor solid. Now, how would you probe this? Okay, so for those of you who are older than probably me, you will remember the story, right? And I see people nodding in the audience, but for all, so please don't spoil it. For the students in the audience, what they tried to do was to create a torsional oscillator. You see, you have a, well, figuratively speaking, a small bucket of helium. And the idea would be that if it's purely solid, so it has to be under pressure. If it's solid, then it has a moment of inertia that's proportional to its volume, right? Whatever you have in the bucket. If a portion of that super solid becomes liquid, superfluid, the superfluid has no viscosity. It can sort of, remain as you try to torsion your bucket around. The superfluid doesn't have to slosh with it. It can sort of stay put. And that ought to, in principle, reduce the expected moment of inertia, right? So there was 2 papers starting from this one, which had probable observation of a superfluid helium flow, and a much more assertive observation of superfluid in solid helium, which came from this group over here. Now,
Same group.
same group. I apologize. Yes, same group. Then there were doubts. So there is this paper by John Rappi, where I think it's just a magnificent exercise in diplomacy. So you read the first sentence of the abstract and says, we have confirmed the existence, as reported by Kim and Chen, of a superfluid state. You say, yeah, great. And then just 2 sentences later, but it's not a universal property and can be eliminated through an annealing, right? So it's sort of backhanded compliment, which tells you, yeah, but not quite. And then there were subsequent papers in 2007 pointing out that there are that if you do the experiment very carefully, there were some pitfalls. I am not qualified to tell you this in detail. If John Sanders was here, he would probably tell you in much more detail what was involved and why exactly this torsional oscillator, why the original measurement was not, or was discredited later. Anyway, you would think that this would be the end of supersolid saga, but then around, 2009, there were several theoretical papers, mind you. Some of them come from, Ashwin Vishwanath, Leon Valens, Alan Paramakanti, who were actually focusing on AMO systems, right? They were interested in optical lattices, and what they had are bosons, which are hopping in your optical lattice, but they also have near neighbor repulsion. Okay, so not on-site Hubbard U, but near neighbor. And they pointed out that at least theoretically, provided you're in this regime, you should be in a supersolid regime. So in other words, if your interactions are sufficiently strong, this V term over here, you ought to have a supersolid. So again, I won't go into the physics of the Bose-Hubbard model, but you expect superfluidity, and you expect also solids in there with well-defined occupancies. And then in between, you could have something which is neither solid nor superfluid. By the way, if you now do this Matsubara-Matsuda transformation backward, the one I already told you about, and you ask, well, what is it in the spin language? It becomes this. And this condition of a supersolid simply tells you that the xy component, the perpendicular component, ought to be smaller than Jz. So all you need is an Ising magnet, or not completely Ising, you do want to have some xy component, but as long as it's strongly Ising, it ought to realize a supersolid. And that was
I
why.
got a little lost.
Yes.
What physically is J perpendicular over JZ, and how does that differ from minus 2T over V? I'm sorry.
No, that's a good question. So you see, if you were to transport this back, this density-density interaction relates to SZ multiplied by SZ, because you see this B dagger B is a boson density. So this term over here maps to SZ, so Ising exchange, and this hopping term maps to S plus multiplying S minus, which is sort of XX plus YY. So instead of a Heisenberg model where all these J's are equal, you say, oh, I want to have an Ising anisotropy, exchange anisotropy. Okay, so not crystal fields, I'm still spin half, just Just Ising.
Because I had the perfect one if it was CEF.
Yes. No.
So this is hardcore bosons, and then you get some somewhat insulating states with some fractional filling.
Precisely. That was the claim from the theoretical papers. And that is why in these papers the experimentalists. Yes, please.
How do they define, is it the same definition as supersolids as was used before, given that here there's an underlying lattice?
Very good question. So how do you even define a supersolid, right? So how do you even think about this? I'll tell you, to be honest, I'm not qualified to tell you what the AMO theorists had in mind when they wrote those papers, but I tell you what this experimentalist had in mind when they wrote the word supersolid. You see, if you look at the data, so now let me show you some data. So this is a neutron spectral data, similar to what you saw in the talks by Pongchen, where the vertical axis are the energies and the horizontal axis are the Q momentum. And you see the evidence of Bragg peaks, and you would see it also in elastic scattering. There are definitely Bragg peaks. Your moments definitely order. If you go back to my language from the first part of the talk, what does it mean? Oh, ordered moments simply means that you have Bose-Einstein condensation. So that's your superfluid. Okay? You could also be more fancy, talk about spontaneous U1 symmetry breaking, talk about this as being Goldstone modes, but it all amounts essentially to this. Now, where does the solid part come from? It's the fact that you see you have, in the absence of XY moments, you have an Ising magnet. So Ising means up and down. If you remember example from the public lecture, for those of you who went by Seamus, he drew a triangular lattice and pointed out, as people usually do, that if you have triangular lattice and you're trying to put Ising spins on it, you end up with frustration, right? Problem that was theoretically solved a long time ago by Greg Vanier, who pointed out that you can't do it with any classical configuration of spins, you ought to have some residual entropy. So what do the SZ components of the spins do? Well, they try to do the best they can. They try to order sort of up, down, but they cant a little. And this degree of canting is allowed to them by the XY component, albeit small. And so what you see is an enlarged magnetic unit cell, and that's the interpretation of a solid, that there is some sort of, yes, you start with a lattice, right? So then what do you mean by a solid on top of solid? Well, it's sort of enlargement of the unit cell. Moreover, it turns out, as I will show you, in certain cases you also break the rotational symmetry. So you have a C6 symmetry of a triangular lattice, you could rotate by 60 degrees, and it turns out that two directions that are 60 degrees apart become inequivalent in this supersolid phase. Okay, so that's the experimental evidence, and okay, you could stare at this, but you know, some people here are much more qualified than I am looking at that like Pongchen. So that's the claim of supersolid, okay? Now, it seems that essentially all I need is an Ising magnet. In this particular case, the value is large. It's about 14, so I have a tiny moment of XY. You're saying, well, if it's almost Ising, then the classical theory should work well, right? I mean, I just have Ising magnets, right? So quoting from Andriy Nevidomskyy in their discovery paper, he pointed out, well, actually, no. If you look at the spectrum, instead of nice, sharp spin waves, you have something, for those of you who are used to looking at this, you have something like what you would expect from a large energy liquid. There are experiments from Bella Lake, for instance, and company, who do this on the chain compounds. Alexei, your audience would know this much better than me. And you expect this filled continuum. That's your fractionalization. Okay, students, so for students in the audience, this is why you should ask me what I mean by fractionalization. Do you remember the story of beta decay? In the case of beta decay, what happens? You have a neutron that decays into proton and electron, right? And if that's the only two outcomes you've got, the energy and momentum conservation would tell you you have unique outcomes, right? So if I know the energy of the measured proton, I ought to know what the energy of the electron that comes out also is. When experimentally, and we are talking about this, what, early 1930s when this was measured, they found that there was a discrepancy. There was something didn't add up. There were multiple energies. So if you think about this, this is energy, this is momentum. There were multiple combinations of energy and momentum that if you add those two, you could end up basically filling sort of a continuum, right? Now, how to explain this? Apparently at the time, I'm blanking out on who said this, but people went as far as to suggest that the conservation of energy was violated by quantum mechanics. I mean, if you think about this, there is Heisenberg uncertainty principle. You oughtn't be able to measure energy exactly, right? There is delta E, delta T larger than h bar, so maybe that was the reason. And it was actually Enrico Fermi who suggested that no, there may be a simple explanation. There might be another particle involved. The energy and momentum is still conserved and obeyed by quantum mechanics. And that other particles, he called it, it has to be something neutral, otherwise it would have been seen in the tracks, right? So he called it, remember, he was Italian, so he called it neutrino, sort of a small neutron, right? And the name stuck, right? Okay, so the idea here is that when you irradiate this with neutron, instead of a single spin flip, which would be well defined, that spin flip fractionalizes into two particles. I don't need three in this case. I don't need the proton, the neutron. Let's just focus on two. If I have two particles, I have more leeway. I could add them such that I preserve the energy and momentum, and that's what filled this in. Anyway, the point Andriy is making, that this looks suspiciously like that. It doesn't look at all like something controlled. Here's another quote from a theorist, this is from Frédéric Millat at EPFL in Lausanne, who said that the spin wave theory is just never correct in the system. This is a quote from a couple of weeks ago at the HFM conference. All right, so how can one do better? I'll posit to you this. This gentleman, I don't know how many of you know him, Nati Zyberg, is very well-renowned field theorist at the Institute of Advanced Studies. And when he was giving a talk in 2015, I wasn't there in person, but I watched the recording, he made the following claim. He made an addition to the Hinchliffe law that if the answer in the title is not yes or no binary, but something like this, how can one do better? The answer is like, I have absolutely no idea, okay? So this is what Nati posits. Now, tongue-in-cheek, the title of Nati's paper was What is Quantum Field Theory? So, if Nati doesn't know, I happen to have to teach QFT next semester, what am I going to do? All right, so I'm going to try and disprove Nati's, this is a hypothesis, right? This is Aristotelian way of thinking, in Seamus's words, right? So it's not a law of physics, it's just, okay, so I'm going to try and convince you that I do have an idea and one can do better. And in order to see this, let's go back and ask how in two-dimensional magnets, how do we make progress theoretically? And a lot has been done. Primarily the numerical techniques, because unlike 1 + 1 dimension where you could use Bosonization, as we've heard 2 talks prior from Polina, here it's much harder. So people have suggested a bunch of techniques. Variational Monte Carlo, apologies, this looks like a lot of abbreviations, but for those of you in the know, this stands for variational Monte Carlo, density matrix renormalization group, functional renormalization group where you decompose your spins into pseudo-fermion first and then treat that problem. Then there are kinds of network methods with fancy acronyms like infinite projected entangled pair states. I'll talk more about those. All right, all of this is well and good for the ground states. But remember, when you measure the dynamical properties, this is what you measure in a neutron measurements. You need to have frequency and momentum. And this quantity goes under the name of spin structure factor or dynamical spin structure factor. It measures basically correlations between the spins, not just at different points in time, but with dilation, not dilation, wrong word, with retardation. So I measure this spin here at position R at time t, and this one at R prime, but at a later time. Okay? And I want to know how they correlate. If you Fourier transform this from time to omega, you get this. So it's only very recently, and I won't go into too much details, but recently, we're talking about just before the pandemic, there are several papers suggesting that you could try and do this with some approximations. Both of those turns out suffer from the finite size effects. Again, for experts, this is because you put it on a cylinder in case of DMRG. The circumference of the cylinder, you're forced to make it finite, otherwise the calculation grows exponential. Anyway, it's arduous and difficult task, and our approach is to try and do better. We're going to use what I call this acronym I told you about earlier, and the key here is infinite. So we're going to work directly in thermodynamic limit. It's not like Monte Carlo where you do it on a size 10 by 10 and then 15 by 15 and then 20 by 20 and you do 1/L analysis. So how do you do this? Well, the idea is that you explore translational variance. You say, look, I'm going to try and tile my entire lattice by tensors. Okay? So for those of you who aren't used about this, let's think about this way. If you want to describe a quantum mechanical wave functions, what is it? Well, it's a linear superposition of, let's say, up, up, down. So this S0, S1, the up-down components. Okay. Now, the coefficients of the wave functions is what's not known. For instance, if this was a ferromagnet, I could choose all of this to be up, 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 choose this coefficient to be 1, and I'm done. But if it's the soup of, of quantum entangled pairs, like in the quantum spin liquids, then there are many, macroscopically many contributions to these wave functions with some weights. How do you kind of capture them? So the idea is that for each contribution, so for each value where this vertical, this could be up, this could be down, this is up, I'm going to assign this coefficient, but I'm going to assign it in a clever way by saying that actually it depends on the matrices. And these matrices have 4 degrees of freedom, left, right, up, and down, and they're all internal, they're not visible. It sort of reminds me of trying to construct the fabric of space-time by saying that there are some hidden variables. And the idea is that you not trace them out. So in the end, what you're left are just these vertical bonds that could be up or down, and that's all what you're going to measure. But secretly, under the rug, there is a lot of this internal degrees of freedom, and those are captured by tensors. Now, why this idea came about, I could give you a separate talk about methodology, but here I'll just point out that what you do in practice is that you tile these lattices, and of course you can't do truly infinite system. So when people say they do infinite IPAPs, which is what we're doing, what they really do is this. They say, look, the side A is the same everywhere, translational invariance. I'm going to just pad it with what T and C here stand from the tricks used in exactly solvable system in StatMech. As are called T matrices, and C stands for corner. And so these corner transfer matrices are the tricks that were used by the likes of Baxter and, Sutherland, who came up with these techniques to try and solve problems in StatMech. And so here you do something similar. You ask a question essentially of finding such combination of corner and transfer matrices that could be different in different directions, such that if you were to do sort of the self-similarity, if you were to enlarge this to this, you stay at a fixed point. You could imagine doing it iteratively. For those of you who are experts in DMFT, like Jan, this is similar to the embedding idea. You take a single Kondo impurity or Anderson impurity model because you don't know how to solve it on the lattice. You surround it by a bath, and then you do a self-consistency to make sure that things works, right? And that's how DMFT, in principle, is also infinite thermodynamically. You don't deal with finite lattices, okay? Okay, so all of this was theoretically posited about 2008, not that long time ago, and it was actually more recently that people were able really to make progress about this. So for instance, just to give you an idea, Uri Hasik was a collaborator for many years. He actually was inspired by ideas from Facebook. Those guys were trying to use neural networks for images recognitions. And this is before the LLMs and ChatGPT breakthroughs. And so they had to write some particular routines about differentiating like giant neural networks. So what did Uri do? He borrowed some of the routines, so actually referenced their libraries that were made public, so-called PyTorch for those who want to know, and they use them to do so-called automatic differentiation. So the point is this: you have this many tensors that depend on many parameters. If somebody asks you, I want to know first derivative of energy with respect to changing one of the, 40 parameters in this tensor A, how would you do it? Well, you could take small differences, right? Just, change this a little bit, compute this, find a difference method, right? The problem is that you always suffer from the fact that you're doing it approximately. Right? Then you have to worry about the accuracy. But what you could do is to say, wait a second, but all we are doing, this A technically was made out of some multiplications and additions at the level of linear algebra. So I ought to be able to literally take derivatives analytically. I don't know if you follow, but the idea is that instead of doing it numerically, you say, oh, I have to take derivatives and go basically follow the chain rule all the way from the beginning of how I was adding my numbers. That requires going almost down to the assembler level to how the operations, the binary multiplications and additions were done on your computer, and then you differentiate and go back up the chain until you get the final result. Anyway, thousands of people at Facebook worked this out, wrote these libraries. We were able to piggyback back on those, and that's state of the art. This only appeared around 2022, okay? So this allows us to deal with larger systems. Now, what are the examples? So for instance, this is one example. Remember I told you about square lattice G1, G2, G3? This is a quantum mechanical problem. I told you it's very hard. If you don't apply field, you don't have those fancy tools I told you and those theorems. So now you have to do it numerically. You have an AL phase, you have what's known as a valence bond solid, but right in between you have a theoretically postulated quantum spin liquids, right? So it's this narrow regime that if true, if you have a square lattice, as long as there are some sizable G2 and you're in this regime, in principle, maybe there is a spin liquid there, okay? Here's another example that I've done with my student Yi. You take spin 1 system, we are not limited to spin half, and you could study what happens on bilinear biquadratic model in 2 dimensions on a square lattice. And there again, there are interesting phases. There is so-called quadrupolar phase, sometimes called hidden order phase. You have an AL phase, you have some dimer phase in between. You could do even fancy, and I mean, for those, I could explain later why we're interested in SU3, not because we wanted to study quarks, but there are interesting connections to sort of this color models where you have SU3 symmetry, and there are some interesting quantum spin liquids that we discovered there as well. Yes?
Have you tried it on something like a tire model, where you know it's a spin liquid, that you can do it exactly, but you want to see if the method works?
Not right. So I know other people have used tensor networks to do it on a K-type spin liquid. As long as you're in a gap regime, so you know, outside of this inner triangle where it becomes gapless, then the answer is yes. You do see exponentially decaying correlations. It's basically zero radius.
But once you go to the gapless,
that's when it becomes very hard.
becomes hard.
That's difficult. And
no, that's a little bit strange because although it's got gapless excitations, its spin correlation function is actually short range.
Right, but
you'd have thought that it would still get it right.
Right. But so you see, if you look at, for instance, dimer correlations, those start decaying.
Right. I see.
So that's what, yes, but indeed. So for instance, the reason why this is very hard, this was a brute force combination of quantum Monte Carlo and tensor networks, is because this is going to be gapless. And how do you know it's gapless? You have to increase so-called bond dimension of your tensor networks, which is very hard in practice. Or in the case of Monte Carlo, you have to increase system size and make some fits and hope that as you go 1 over correlation lengths, that the gap goes to 0.
Just to connect up with the talk we had earlier in the week, what about the Kagame lattice, the Herbert Smith like to do? What do you get there? Do you get a gapless or a gap state?
It's hopeless to try this. Well, that's not true. People did try in a Kagome lattice.
Yes.
This is a Kagome lattice, but the reason we focused on SU3 is because surprisingly the problem becomes simpler. Anyway, you take spin half and you try to do it on a Kagome lattice. You end up, well, GMRG studies by several groups, including both Steve White and Uli Scholberg, initially posited that it's a Z2 gap spin liquid. That's what in his talk yesterday, Seamus Davis was trying to write. Remember, he postulated the existence of a gap. And later on, there were techniques using so-called infinite DMRG from Yin-Chin He and Frank Holman and Zalapov, where they pointed out, no, actually, if you do it carefully, the gap might vanish, but it's certain momenta in the Brilliant zone. It's tough. When I asked Yin-Chin He, at some point he says, look, I don't think this question ever is going to be settled, because you could always say that there is a gap, but it's so small that you need to go to even larger system sizes to detect it. All right, I'm not going to go into this debate about what happens on a Kagome, but instead let me go back to my Mouton. So here we are talking about the system which is Ising, supposedly simple with some transverse components. This is what experimental magnetization looks like. In the first part of the talk, we were all over here, see right before the saturation, and this is where I could use the kind of techniques which were pioneered by Belayev. Oh yeah, what is my time?
I forgot. I think we're going into the infinite time limit.
Well, I know we started 20 minutes late. I know that 17:10 is where we would have finished had we not started late. How many?
We've got 15-ish minutes.
15-ish minutes. Oh, I'll finish before then. Don't worry. There will be time for questions if you have more. All right. So you see those regions that are highlighted here in some fancy colors. Those are results where, according to our IPAC calculations, you find this blue here stands for the staggered magnetization. That's your superfluid component, which is over here. And now the bit, which is the red, which is also non-zero, that's your supersolidity. Remember I told you that the spins don't quite know how to arrange themselves. They form this sort of Y pattern at low fields. And so you have to assign them. I mean, here I drew them kind of on top of each other, but they correspond to A, B, and C sublattice. Right? So if you imagine taking a pass through a triangular lattice, and you arrange the sides in ABC in some fashion, A would look leftwards, whatever, northwest, this will be northeast, and C would look to the south. Right? So there is some non-collinear but coplanar arrangement of spins, and that forms this root 3 supersolid. All right.
Andriy, if
Yes.
if I look at your magnetization, that's pretty traditional metamagnetism. And you know, this is stuff that, for example, with Amelia at your place, we looked at in detail. What about that MH curve is magical or special?
Well, devil's in the detail. Okay, so
No,
first
but I
of
just
all,
say experimentally, I look at that, it's okay, I've got a nice metamagnetic transition from anti to up, down to up.
Yep.
Yeah,
So-
first order, right?
Well, actually, yes. So this transition is first order, but right around over here is where you see the superfluid phase. This transition here is actually second order.
So you
Well,
don't
let's-
see here plateaus because there is small temperature.
Correct. So in fact, if you look at the data, 0.19 Kelvin, I mean, that's pretty close to a plateau. If I were to remove the red lines, that is at 1.3, this would actually line quite nicely. You know, from about 3 Tesla to about 12, you form a 1/3 plateau.
And the strongest hysteresis, right? It's going up and down, like the black is up, the red is down.
That's first order nature,
It's
right?
first
Yes. Yeah.
Are you excited about 1/3 or the plateau?
No. So the plateau is well understood. There is no mystery about that.
Right.
Just before the plateau, like right over here, is where you start seeing this supersolidity, which is due to the fact that your XY components form a particular
But it's
pattern.
also first order, right? Due to hysteresis, right?
There's big hysteresis.
Yes,
Very big.
yes. So there is some, depending on how you do it, whether you ramp up field up or down, there is hysteresis, I admit. Yes.
No, that's the black and the
Yes.
red.
In our calculations, we don't see hysteresis. Then again, you know, there could be material differences there.
What do you
Alright.
mean by superfluidity?
So, like I said, superfluidity is a fancy word in this case to just simply say that there is a non-zero value of x and y components of spins. So this blue blip here in the calculations just tells you that, yeah, the spins are mainly ising, but you see this canting over here, it's coherent across the lattice. You see, because what you could have, see if I can do this. All right, so you have the markers that go like this, right? And you say, well, happens on A, B, C pattern. So really I'm cheating. This is A, this is B, this is C. I should have them spatially, but I don't have that dexterity. So I'm gonna pretend that happens locally here. Now somewhere over there, it's still in the same pattern. There's no reason why it couldn't be slightly rotated. Energetically it's the same. Maybe over here it's rotated a bit more. If you know about the Z component, just look at it from above, you ask, well, at this point of a lattice it looks like this, and maybe as I go it rotates. Maybe it's randomly fluctuates. Phase rigidity tells you the phase is the same. I look over here and these two spins, I mean they can't, but they'll say that they lie like this. And I look way over there by the door and they still look like that. If you think about this plane as a phase of your superconductor, that's like saying, oh, here I have a phase, I don't know, let's say 0. And up there the phase is also 0, but that's my phase coherence. So, like I said, it's maybe an unnecessarily fancy language. Helps sell papers apparently about supersolids. Not mine, I'm talking about experimentalists. All right, so, okay, but what about excitations? I mean, all I've told you about was about ground states. Excitations, what do you do? In order to do this, we do a trick, which is where you modify your PACs, your cleansing networks, by inserting an imposter. You change one of the sides and say, I'm gonna mess it up, okay? And I'm not going to tell you how to do this. You just put some random tensor over there, and then you optimize the state, and you compute the energies. In other words, in a fancy way, what you're solving is basically eigen-mode problems of inserting this extra side. It's not unlike looking for eigenmodes in the case of a phonon calculations, right? So you tap it over here, you hear sound with a certain frequency, you have to solve for eigenmodes with different energies. That's what we do. And you could do it as a function of k, and that's how you get the dispersion of omega and k. I can give you, and will give you a bit more detail of how you would do it. So the quantity you want is this dynamical spin structure factor. And after everything said and done, this is just inserting the resolution of identity. You're manipulating these B tensors. And if the space were fully complete, if you could insert, the full Hilbert space completeness, essentially you end up with a relatively simple formula. Remember I told you about this eigenmodes? This would be the oscillator frequency, that's Q dependent, and this would be what people call oscillator strength in like optical analysis. So this is like a single mode approximation where you're looking at oscillators with different frequencies and with different weights, and at the end of the day, that's all there is. What's hidden under the carpet are all the complex calculation of having concatenate all of these tensors, which takes, even using modern GPUs and this Facebook algorithm, it still takes weeks on powerful supercomputers, okay? So what do we get? So here's an example of a benchmark. You take triangular lattice and you compare what we got using our technique with what Federico Becker gets for H Monte Carlo, or what Jules Moore at Berkeley gets from finite DMRG. And yes, there are differences. For instance, Joe Moore does a time evolution and then Fourier transforms. And when he does this, things get smeared and he has sort of nice color scales. Federico does more close to what we do. He has sort of discrete branches of particular energies because we are solving generalized eigenvalue problems. So strictly speaking, we have discrete set of eigenvalues. Okay, so they're not continuous functions. But let's look at what we get in this material. So this is an experiment. And if you were to do this, so this is what the theory would look like. Okay, it doesn't look quite as nicely resolved in Q momentum simply because for each Q, you have to spend a week at a supercomputer trying to get this data. But you get something that sort of resembles the Goldstone mode and the corresponding Bragg peaks. You also get something which people call a Roton minima. If you look at the M point in the Brimmer zone, it's sort of halfway between the two gamma points. You get sort of a softening of the mode, which resembled what people see in helium-4. Again, maybe it's just a semantics. I don't see a clear origin of this. It's not the same Roton as in helium, but okay, let somebody else be the judge of that. There's also something interesting. You see, I showed you that if you look over here, you see a Goldstone mode, but there's also something else. There is something which people call sometimes pseudo-Goldstone mode. It's a higher energy mode, which comes not because there is a spontaneous symmetry of the Hamiltonian you've broken, but because there is an accidental degeneracy between ground states. It turns out that this Y model has an accidental degeneracy, accidental symmetry, where I could do, gosh, a clever rearrangement on a size that looked like this and tilt them at a particular angle, and it changes A, B, and C. You see my, yes, this report. We need Sam with his piano playing skills. Anyway, there is a way where you could show that there is an accidental degeneracy or accidental symmetry. That's not the symmetry of the Hamiltonian, but symmetry of your ordered state. And there is, I could give you an entire talk about this. It's called a pseudo-Goldstone mode. It's a soft mode associated with this accidental.
So you're talking about longitudinal mode?
Huh?
You're talking about longitudinal mode?
No, it's another symmetry that's not part of your Hamiltonian that has an accidental.
It's a classical symmetry.
It's a classical symmetry in a way. And it turns out there is a soft mode associated with it, but it's gapped. And that's called the pseudo-Goldstone mode. We could measure what that is without going into too much details. It ends up being somewhere between 50 and 60 MeV. And this is before we even know the experimental data from Zhaludov. So there was a conference a couple of weeks ago where I presented this result, and then there was experimental talk later by Zhaludov who showed this value. So it seems to match quite well.
It should be called a Shendar mode.
Ah.
So this was first proposed by the Russian physicist Shendar.
Okay, thank you, I didn't know that.
Stick with Fermi, call it a Magnino.
All right, so this is, by the way, one of the last few slides, so I'm not going to torture you more. Just one other thing. If you look experimentally at this, there is something interesting. You look at omega versus Q, and you see this flat, almost non-dispersive modes, which amazingly seem to be quantized at equidistant energies. And you ask, well, what is that? Right? If you show this data to somebody who, who's not a neutron experimentalist, they will say, well, I don't know, it could be, I don't know, it's Q independent, so maybe it's a crystal field level, right? Something like this sort of flat, like what would it be? But why would they be sort of equally, equally spaced? When you do our calculations, we get something very similar. You have this mode, and then you start glimpsing, and you realize that actually these objects are a little bit dispersive, and the width of them is of the order of your JXY. Remember, the transverse component is about 14 times weaker than the Ising, and so the bandwidth of this mode is weak. Now you ask, what about the splitting between them? So it turns out that the splitting between these modes actually corresponds to the value of Jz, the Ising anisotropy, or Ising exchange. And really you could think about, so this is what the advantage is, that you know how you could compute the frequency of this eigenmode of the sound? You could also visualize it. So here's a real space visualization of what this point looks like. Okay? So if you stare at this, sorry, let's go in. Oh, okay, you see I'm already at conclusions. All right, so sorry about this. There is clearly...
I think it's now time.
Yeah, I know. Okay, let me just point out that this thing corresponds to a single spin flip. That's your single magnon. If you look at this energy, it actually has, if you integrate this over, there are effectively 2 spin flips, but they're kind of floppy. They're disorganized a little bit. If you go even higher, which is harder to see, but there's a faint mode, the screen is hard to see here, but I can see it on my screen on the computer. There are sort of 3 spin flips associated. So this is like a single magnon, a bound state of 2 magnons, a bound state of 3 magnons. All right. So this can capture not just a single mode, but can capture also bound states. All right. I'm done. In conclusion, I told you about this supersolid, which again, maybe you disagree with semantics of how to call this, but morally what they see is essentially some enlargement of the unit cell with long-range order in plane. And our calculations, numerical breakthrough here is being able to do dynamics, is able to reproduce and show what they saw experimentally. And I'll stop here. Thank you.
Okay, we're really over time, but time for just a little bit first. Okay, go for it.
So, I mean, there is also the DMRG work by Joe Moore on the isotropic triangular lattice model, right? So, and you have the anisotropy. So, if you put or sketch a phase diagram where on the other axis, so your field is on the other axis, let's say Jz minus Jxy, how does it evolve? Just to see. I mean, the kind of long-range order
I think
eventually ceases to exist, right? If you go closer to the isotropic limit, where you expect some.
All right.
Some U1 quantums for liquids.
Okay. So I don't want to. For those people who don't care about this, maybe we should. But yeah, I was about to show you the. Do I have it here? There is a phase diagram that I could show, but I don't have it in. I thought I had it in my extra slides, but no, it's not here. All right.
Good. No, actually, Eva was first.
Okay, thank you for this nice talk. I have 2 questions. One is about the very first part of your talk, where you talk about the BKT transition that goes with solid. So typically in a 2D BKT transition, quite often it proceeds by 2 steps. First, you go from algebraic or translational order to exponential translational order, and at the same time you go from long-range orientational order to algebraic orientational order. So that's the exotic phase, and only then you go to the next phase, to the disordered phase. Do you see something similar here?
Okay. So my knowledge of the hexatic phase is vague. I remember reading those old papers, I think by Halperin and company. I'm not sure I'm qualified to answer this. Let me tell you that from our perspective, we are working in a limit of small temperatures. We are way below BKT transition. We can do calculation at finite temperature, for instance, conclude how this boson density scales with temperature as a power law, but all of it is only true way below the BKT. The kind of method we use does not let you talk about vortices and anti-vortices unbinding, right? That's a topological scale that's beyond what you could do in our one loop calculation.
But you can go at low temperatures, you can go, but changing your J, you can go into the disordered state,
yes,
right?
because
Without
BKT,
going- right.
So the most precise thing I could tell you is that the BKT temperature goes to 0 right at the Lutsch's point. So as you cross this, something strange happens. It's no longer BKT. What is it? Turns out that this algebraic spin liquid I told you about.
Okay.
It's a
My
higher
second
dimension.
question,
It's a higher, at that point it's quantum, so it's a higher dimensional phase transition.
so you don't have.
So probably you don't have the same
It's
features.
just one, a sharp transition, you lose the
I
order.
defer to
Usually.
Andriy, but it doesn't have to be the same as in a
Yeah.
turbo.
Yeah, as a classical. Yeah.
My second question is about the super solid. I have no idea why, I mean, it seems to have no connection to the Andreev super solid. The Andreev super solid is something really weird, where you have long range translational order. At the same time, the thing flows like a superfluid under pressure gradient, which you see with the torsional oscillator. And
Or
when
don't
you-
see, according to Paul.
Well, no, the paper that by Repi,
Yep.
this is exactly right, because the way I understand it, the thing that flows like a superfluid, it's a dislocation fluid. So it's a fluid of dislocation in this solid. And so it would depend on how you prepare it. So Repi saw it, and then he annealed his crystal, killed all the dislocations, then it disappeared. It makes perfect sense. Now, I don't understand why increasing the unit cell, the size of the unit cell, can be called a supersolid. Like when we do a moiré, you're increasing the supercell, the unit cell.
Oh,
Do we call it a supersolid?
you tell it, well, I don't know what the name is. You can enlarge unit cell. If you now have superfluidity in your Moiré system with artificial large cell, you could call it maybe a supersolid. I don't know.
I think if you want to talk further, it will have to be
Over
in
B.
that corner on the corner. Let's thank you. Okay?
It's a bit different, right? Because
So I always enjoy listening to you talk.
Yeah.
You give excellent presentations.